Swayam Prabha. Digital India. Educated India.
Hello and welcome to the discussion sessions of production technology, theory and practice. So, let me remind you that in our last session of discussion, we started discussing the specific energy in grinding, and we said that the specific energy in grinding is very high, and I discussed it with you that there are basically three reasons. One is the size effect, and the size effect means that when the T1 is small, uncut thickness is small or thickness is small, then the specific energy becomes very high. So, I have shown it to you graphically how it can be presented. And the other points are that when the grinding process takes place or abrasive machining processes takes place, then initially the grains do not remove the material, but they rub more. Okay. After that, as the normal force increases, then there is a ploughing action instead of metal removal action, and with further increase in the normal load, the material removal takes place. So, since initially there are the rubbing and the ploughing, so that consumes a lot of power, lot of specific energy. So, along with the size effect, that during the grinding process takes place at a very thin T1, at a very thin depth of cut, let us say, where the imperfections do not exist and the material behaves almost like an ideal material, the specific energy goes very high in comparison to any other normal processes like turning, milling, drilling, etc. Having said that, next we told about the wear of the grinding wheel, and we said that in grinding wheel also, the initially when the grinding wheel comes in contact with the workpiece, it happens like the single point cutting tool, that since all the grains are sharp and the stress concentration is very high around the sharp edges, as soon as it comes in contact with the workpiece, they get a rapid wear. So, wearing action of that, those sharp grains becomes very rapid, and that was the initial wearing action. So, we said that that is the, if you look at this slide, we said that this was the initial break in. After that, we said that the steady wear takes place, because there apparently a self sharpening phenomena happens, that as the grains wear out, they get dislodged easily from the surface of the grinding wheel, and therefore, this steady wear goes for a long time, and this is specified as the self sharpening of the grinding wheel. After that, when the wear takes place quite a lot, in the sense that the flats went more and more, then there will be a catastrophic wear and wheel needs the reconditioning, because after this point the wheel will not provide the specific machining quality that is desired. Because of the worn out grains on the surface, because it may be the glazed surface, because it may be the many other reasons, because the wearing action has taken place, including the initial break in and the steady wear. So, at that point the wheel needs dressing, and the dressing I have already explained to you that wheel dressing is also required when the wheel is glazed or the wheel is loaded, to remove the worn out grains or the chips which are clogged in the voids of the grinding wheel surface. So, therefore, these are the phases that I have discussed with you, that these three phases come within the grinding wheel during the material removal. Now, these are explained that there is a self sharpening. What is the self sharpening? Okay. And there is practically no wheel dulling in this steady wear. These things have been discussed. Then we started discussing in our last session that how the grinding wheel wears out. So, these are the grains which are bound together, and the entire thing is a grinding wheel which is in contact with the workpiece, and it rotates along with the VF, and then the material is removed from the workpiece surface. So, like it is shown here, that each grain will remove a small amount of the material in terms of small chips. So, when these grains rub along the workpiece and removes material from the workpiece, there are three types of wear that I have mentioned to you in our last session. So, let us see that in more details. First is the attritious wear. Attritious wear occurs at the grain workpiece contact surface. So, this I have shown it to you earlier in the last session, that in these contact areas, in these contact points where the grain is in contact with the workpiece while removing the material, gradually it wears out. Okay. So, this wearing action is the gradual wearing away of the sharpness of the cutting points, resulting in the formation of wear flats on the grain tips, as I have shown it here, that there will be kind of a flat formed. These are the wear flats because of the wearing action, okay, gradually on the grain tip. So, this kind of wear which happens at the contact point between the grain and the workpiece, this is called the attritious wear. Okay. This is one type of the wear. Now, it is due to the microfracture of the cutting points, because points are still sharp, okay, plastic flow at the grain tips, and maybe because of the crumbling of the sharp edges. All right. So, this is overall the result is that this is a gradual wearing action of the cutting tips which are still sharp, and they started removing the material. So, these are the three things, that is microfracture, okay, plastic flow, or the crumbling of the sharp edges. So, because of these three factors, all right, the grains wear out, and this is called the attritious wear. This gets aggravated due to high temperature obtained in grinding, of course, and the flat becomes more. All right. Once the flat is made, then it creates more temperature, and along with the temperature which is anyway created because of the grinding process, this flat becomes more. All right. And the attritious wear increases. Next type of wear is called the fracture wear. This happens along the BB line within the grain. When the stress on the grain increases to a sufficiently high value, the grain fractures into fragments and fresh cutting edges are exposed. This is called the fracture wear. Okay. Now, when this flat is increasing in the attritious wear, the forces on the grain also will be increased, because the flat is more. So, finally, what happens, that the stress applied or the force applied on the grain, particular grain, will be so much that the grain strength of the grain will not be able to withstand that kind of a magnitude of force, okay, and it breaks, simply it breaks. All right. So, when it breaks, the new grains are exposed, because it will still stay within this bond with this grain, and within this bond in this grain. So, when it is broken, just imagine, it will not be broken in along one line, it may be broken in this way. All right. And you can see that these are the sharp edges which are exposed, and these sharp edges, I am exaggerating that, will actually serve as the new grain, okay, sharp grains, which will have less rubbing, less power consumption, less force requirement, and it will be not providing and not creating high temperature because it is a new grain, sharp grain, all right. So, this is called the fracture wear, it is fracturing along the line along inside the grain. Next type of fracture is the bond post fracture, it happens either within the bond here or within the bond here, all right. When the grain is stronger, so the force is increasing, let us say in this fracture wear, but if the grain is stronger than the bond post, all right, then here the strength here with the bond and the grain, in that case the grains get pulled out of the bond post when sufficient force is applied at the grain tip. Okay. So, when it happens? It happens normally in the soft grains, okay, soft wheels. So, in the soft wheels the bond is soft, okay. Bond is soft means it will allow the dislodging of the grains easily. In that case what happens, instead of grain breaking within the grain surface like this, like the fracture wear, it will actually be pulled out from the bond post, all right. Normally it has been seen that where it is actually connecting with the grain bond and the grain interface, it is stronger than within the post, okay, within the bond post. So, therefore, fracture will normally happen within the bond post here, all right. Generally the interface, that is what I said just now, that interface between the grain and the bond post is quite strong, all right. Hence, the pulling out of the grain would be due to fracture of the bond post, all right. That is what I said to you, that it will not be along this line or along this line, okay. It will be along the line somewhere inside the bond, because these interfaces between the bond and the grain normally they are very strong, okay, all right. Bond post this is called, as I said, is the bond post fracture. So, when it is fracturing within the bond post, okay, it is called the bond post fracture. Now, glazing occurs when worn abrasive grains are not fractured away or dislodged from the wheel. As I said that if it is not getting dislodged when it is worn out, then of course, I am repeating that the glazing occurs. Okay. All right, these are some experimental results, I am not going into these details here. Now, let us see in grinding what happens in the as the temperature rises. So, this is the thermal analysis, and this is very important because the grinding temperature has to be assessed. Okay. I am giving you a preamble that why this temperature model is important in case of grinding. Thing is that in case of grinding, the measuring the temperature by any device is difficult, because this process is very fast. There is chip flowing, and then there will be sparks because of the small chips burning, all right. So, therefore, there is a model, that is some sort of analytical model by which we can actually temperature which is occurring during the grinding process. So, why it is important? If we can assess analytically that what is the equation finally of the grinding temperature, meaning what are the parameters on which the grinding temperature will depend, in that case we will have the full control on the grinding temperature. We can control those parameters, output parameters, okay, or variables, and by controlling that we can actually decrease the temperature, output temperature of the grinding process. That is why it is very important to assess the parameters which actually depend, which will affect the grinding temperature. Let us see how it can be done. It is extremely difficult, as I said, to develop a satisfactory analytical model for calculating the surface temperature during the grinding. Apart from the difficulty that we have in measuring the grinding temperature, it is also difficult to directly make a model, all right. We shall therefore adopt an indirect approach for yielding the approximate results. This indirect approach is that it is not very illogical to assume that the grinding temperature depends directly on the energy spent per unit surface area ground. Okay. Meaning that depending on the unit surface area that is being ground, the energy will depend. More surface area ground is more energy, in one word. Okay. So, the temperature is proportional to the energy per unit time or energy per unit surface. So, we can write this in terms of an equation that this theta, which is grinding temperature, is proportional to power divided by B into Vf. This is the area. Okay. So, P is the power. This can be given as area into UC into MRR. Okay. So, I am sorry, this is the MRR because this is the Vf into the width, and therefore, it will be the power is equal to area MRR into the UC, which is the this entire thing is area. Okay. So, B into D is the area and the Vf, area into Vf is the MRR. So, entire thing is the MRR. UC into MRR is the power. Power divided by B into Vf will give you this proportionality, because this is the per unit surface, right. Per unit surface is the whatever we have the width okay, into the Vf is the feed velocity. So, if we do that, then we will find out that this is proportional to D and the UC. Okay, that is the depth of cut, and the UC. UC is the specific energy. Okay. Now, specific energy will write as U0 half of T1 maximum to the power minus 0.4, because you remember that we said that the UC, this is U0 T1 to the power minus 0.4 in general. Okay. So, in case of milling or in case of grinding, as I said, the T1 is the T1 average, and T1 average is 1/2 of the T1 maximum, roughly we assume. Okay. Now, here the T1 is equivalent to T1 average, and which is equal to half of T1 maximum. This is the complete explanation of that. So, this equation is applicable to the grinding process in the following way. Now, the T1 maximum, if you remember, we have derived, okay, and we said that the T1 maximum is root over this factor 8 Vf root over depth of cut divided by pi d n c, gamma g is the grinding ratio, root over d, capital D is the diameter of the grinding wheel. Okay. And the power is given by UC into MRR. UC into MRR is exactly written like this. Okay. This one. So, in that case, the T1 maximum, this value if we put in here and then to the power minus 0.4, then you multiply these powers, okay, and then simplify that, it will be that the temperature during the grinding process, that is proportional to specific energy constant, then it is the depth of cut to the power 0.9, okay, to the power 0.9, you understand that this is minus 1. So, this is 1 minus 1, that is 0.9, n is 0.2 and so on. So, 5 and this will be minus 0.4. So, it is minus 0.2, minus 0.2 goes up to as 0.2 and so on. So, you can find out that these powers can be obtained from here, and this is the final equation. Here of course, we are saying that this is proportional because we are avoiding all the constant values, okay, like this here and so on. Now, let us see what it says, that now we know that as per this assumption that the temperature is proportional to the energy per unit surface area, and that is not a very illogical, as I said, because this is the one I mean this will be the valid assumption. So, therefore, the temperature and also the defects, thermal defects caused by higher temperature can be reduced, so that it can be reduced either by decreasing d, okay, depth of cut, diameter of the grinding wheel, grain concentration in case we can, because we said earlier that grain concentration we are not touching since there is a particular grinding wheel, but if you can change the grinding wheel with different grain concentration if there is an option. So, we can do that so that the temperature in the grinding process could be less, or n is the rotational frequency of the grinding wheel. If we can decrease these 4 factors, okay, or if we increase the table feed Vf, then we can actually reduce the temperature. Temperature in the tool chip interface can go beyond 1500 degree centigrade, which is very high temperature, and when we will go to the lab, you will see, we will show you the grinding process. You will see that there will be tool grinding. We will show you the how the rake face of a grinding tool is reground when the rake face is spoiled or worn out. Okay. So, we will see that always whenever the grinding wheel is in contact and removing material from the workpiece surface, there will be spark, and that spark is actually burning of the very small chips, and the spark, because it is a this high temperature of 1500 degree centigrade. Chip sometimes do not melt because it is flown away at a high speed. Okay. So, it flows away at 1 by 1000 second. So, it is a very high speed, okay, and sometimes it is not melted, it burns up to that point. Okay. Now, this is, I hope it is understood that these are the parameters on which the temperature of the grinding depend, and therefore, we have a possibility of regulating the grinding process, so that the temperature is within the range or within our desired level, so that there is no thermal deformation of the material that is being ground. This is important because let me tell you one more thing, that normally the grinding process is done after the heat treatment. Okay. And after the heat treatment, normally we find that some of the surfaces are distorted because of the high temperature that is involved in the heat treatment process. So, to smoothen those surfaces and to get the accurate surface that is desired, we normally perform the grinding process. Now, therefore, we cannot afford to have the further surface deformation because of the grinding process, all right. And the further deformation can come either because of the very high force involved in the grinding, or very high temperature which is occurring during the grinding. Okay. So, in this case what we have discussed is that there are still provision that grinding temperature can be reduced by manipulating those 5 parameters. Okay. Now, apart from the grinding process, in the abrasive processing, okay, there are processes like honing. Okay. Now, this honing process used for proper finish. So, it is not for as much to remove the excess material, but it is basically for removing the undulations after the grinding, if any. Okay. Undulations means those are the surface roughness. Okay. So, asperities, let us say, bars, let us say BURR bars. Now, to remove them, it is very important because let us say if we have for example, like this, a part like this. Okay. Let us say this is a cylindrical part and here there is another. So, you understand that this kind of a part normally exists in the cylinder of the automobile, okay, in the internal combustion engine. So, that means a piston will go up and down, a piston, let us say I will write it in this way, all right. This is a piston, this will go up and down, all right, and this will be for the automobile to run. Now, when it is going up and down, these are the two surfaces, these two cylinders are made. First you make a cylinder and then you make a hole, make a hole from here, and then you make a hole along this axis, that means this hole. Okay. So, these two axes then will be perpendicular to each other. But then while you are drilling this hole, actually there will be in this joint there may be some bars, that means the unfinished material. These chips are not able to be taken out, okay, and they stick to that. They are called the bars. These are the BURRS, bars. So, removal of those bars are extremely important, and very often these kind of bars, okay, inside this cylinder, and this cylinder may be of very much less diameter. So, that may be very difficult to actually have the grinding wheel, for this kind of thing. So, either it can be then removed by honing or by any chemical technique, okay, or by unconventional machining like electro discharge machining, electrochemical machining, which we will be discussing after this. Okay. Now, in case of honing, normally the cutting speed is low, okay. It is about 10 to 30 meter per minute, and this is the honing hone. This is called it is written here anyway. So, the instrument which is used, device or tool that is used, that is called the hone, HON. So, that is why the process is called the honing, all right. Now, hone itself is a metallic arbor like that, okay, and around this periphery, on the periphery of this outer cylindrical part or the mandrel as it is called, there are honing sticks, and honing sticks are made of abrasive materials. So, these abrasive materials, these abrasive grains are very fine. So, it can be up to 600 mesh, and up to 600 mesh means 0.6 by 600, okay, inch. It is the diameter of the grain, all right. So, therefore, you understand that up to 600 mesh, these are very fine grain, and it will be very fine sticks with the honing sticks with the very fine abrasive grains. Okay. That will remove very small amount of material from the inside diameter of the hole, but it will basically smoothen the surface. It will smoothen those asperities if it is inside. So, if you see here, this hone is actually in other view, it is like this. So, the honing sticks are mounted on this mandrel, and this mandrel is shown here. This mandrel sits on this axis or on this spindle. That spindle is little tapered, okay. Here it is of course exaggerated. This is because when the mandrel rotates or when the hone rotates, it will also go up and down along the length of the hole, okay, along this. So, while doing so, therefore, the honing sticks have to have some kind of a depth which it will be removing, okay, like the depth of cut. So, the depth is given like infeed in case of the grinding that I said. So, this depth or infeed is given by expanding that and pressing the honing sticks towards the walls, internal walls, and that is done by tapering the mandrel or tapering the spindle. Okay. So, when it goes up and down, it actually gets pressed depending on the amount of the tapering that has been made here. So, here is the another view. You can see that this is the workpiece. Okay. This is the workpiece, and here this is the workpiece. Okay. This is the hone. This is the hone, and this is the these are the honing sticks. This is one, this is another, this is the third, and this is the fourth one. These are the honing sticks which are this, all right. Now, here this actually rotates and then it goes up and down. So, this also rotates, all right. So, this goes up and down and rotates, so that the entire length of the internal hole can be actually removed, all right. Now, the grit size, as I said, is up to 600 mesh. So, the grains are very fine, and the pressure which is given on the internal surface of the hole this is about 1 to 3 Newton per millimeter square. This is a very low pressure. So, you can understand that this tapering has to be very gentle, and the maximum material removal is, you can see that 0.25 to 0.5 millimeter, it is very less amount. Okay. Maximum is 0.5 millimeter, but it is 0.25 millimeter, it can also go starting from 0.25 millimeter. Okay. Now, the honing is carried out, as you can see, that at a lower speed, I told you that. Now, this lower speed is carried out because otherwise what happens, the chips, small chips, because it is 0.25 millimeter, okay, it is removing. So, those very small chips can actually get entangled between the honing sticks and the internal surface. And you know, I already told that the honing process is to increase the surface finish, all right. So, in those surface finish will be very smooth, this is actually kind of a polished surface. So, if on those surfaces there will be a scratch made by the entangled very small thin chips, then the surface will be spoiled. Okay. So, therefore, it is actually rotated at a lower speed, so that by vacuum we can actually take out the chips, okay, and the small chips are lightweight, but if it is at a higher speed, that this can scratch before we are able to take them out, all right. Microchips can be entangled, it is written here, with the honing stone to form excessive heat if the process is performed at high speed. Another reason is that apart from the scratching, of course, it will create heat, and then it can actually create the thermal workpiece. Now, in case of honing, the surface roughness also is obtained like that, that means no repetition of the grain marks, okay. And this is done for the retaining the lubricant oil, okay, the fluid lubricant, particularly when we are using the solid lubricant, let us say molybdenum sulphide. Okay. So, in case of bearing, you know that bearings you do not oil. Okay. So, they actually put the solid lubricant and press it. So, it is sealed. Now, that lubricant is sufficient for the entire life of the bearing. Okay. And in that case, if we have a kind of a surface where the grain marks are not repeated, in that very fine undulations the solid lubricant can stay, and for some other parts apart from the bearing particularly, that is very important, because the lubricant will be retained. Otherwise, what will happen is that when the two parts are rotating with respect to each other, then there will be temperature, and at that temperature the viscosity will grow more, and in that case it will be fluidic. Okay. So, suppose the solid lubricant has been applied, so that becomes under the high temperature, it becomes fluid and it will flow away, all right. It will not be retained there, but in case we have the kind of surface that I am saying here, in that case the lubricant can be retained to a large extent. Okay. Now, next process is the lapping, and lapping is an abrading process or abrasive process used for improving the accuracy and the finish. Okay. Laps are made, this is the instrument, like drill in case of drilling, okay, hone in case of honing, lap in case of lapping, are made of material softer than the workpiece material. So, it is a kind of a plate, all right. It is a kind of a flat plate like this, and there are these grooves, okay. These grooves, straight grooves, 90 at perpendicular to each other, 90 degree to each other, all right. This material is softer than the workpiece material. Straight narrow grooves are cut at 90 degree angle on the top lap surface, and this surface is charged by sprinkling the abrasive powder, and the abrasive powders are very fine powder. This powder may have up to 1200 grit. So, this is, as you can see, even finer than the abrasive grains used in honing, all right, and suitable fluid. So, what is done is, here you sprinkle some kind of abrasive powder plus the fluid, so that the powder, so such a fine powder does not flow away, Okay. So there is a paste form, that is this abrasive powder and some sort of mineral oil. So that will make a paste and put it on this surface. So the surface will be covered by that paste, and then the workpiece is then held against the lap and moved in an unrepeated path in the form of 8. So suppose there is a part here, okay, this is the part, small part. So this will be repeated like this, it will be moved in this path, okay, so that the again to get a surface, like we said, that the grain mark should not be repeated. All right. So this is the part, this is the part, and here this will be rotated like that, it will go like this, go like this, this in the form of 8. Okay. Now in case of lapping, we have the hand lapping, as we said that here you put the part on the plate, and the plate once again is a soft material, at least softer than the part. Okay. Then you hold the part by your fingers, this is the hand lapping, and move it at a path of 8 on this, okay, with a bit of pressure, and that pressure I am coming to that, all those the parameters. Okay. Now it can be also machine lapping. In case of machine lapping, these small parts, normally the lapping is made for small parts. It can be of course the part which is stationary, which is relatively bigger, like I said in case of automobile cylinders. Okay. It can be hole lapping, all right, or it can be shaft lapping. So for shaft lapping and the hole lapping, you hold it with that paste, okay, and then you can go through and forward and backward, and you can rotate the shaft. So it will be actually lapped, kind of a polishing. Okay. Similarly, for the hole lapping also, you can have the lap inside and then rotate the cylindrical part, so that the internal hole of this can be polished. Now in machine lapping, as I was saying, that the small parts could be taken in a bag, okay, that is a it's a kind of a bag which will hold them, and then the top surface will be exposed. Okay. So that bag will be packed with the parts that will be kept in between the two plates, okay, lapping or the laps, and then the lapping can be done by moving the plates, and the parts will be lapped. Parts will be having the smooth polished surface, that is the machine lapping. In machine lapping, lapping plate or lap becomes a rotating table. The part to be lapped are confined into cages that impart rotary and gyratory motion at the same time. Okay. So it will, gyratory motion is, you understand that this will actually do a motion like this. It will also rotate, and not only the straight rotation, but rotation and gyratory motion. All right. Then only it is done because of the fact that the entire all the surfaces of the part can be polished equally well. Okay. Covering the entire surface of the lap. Parallelism is maintained by having a stationary lapping plate on the top of the workpieces. So there will be a plate, and on the top of that will be lap, and lap rotates and gives a gyratory movement, and to keep the plate, keep the parts in contact with the lap, on the top of the parts, on the top of the cage, there will be another plate which will be actually guiding or supporting the parts to keep them in contact with the lap. Okay. Hole lapping is similar to honing, consisting of sectors ranging from 2 to 6 mounted on the arbor and expanded by springs. Okay. Holes are rarely lapped because it is a slow production. Yeah. Now in the hole lapping, as I said, that this will be something like hone, okay, but of course those ticks will be much finer. It is up to 1200 grit size, okay, or the SN number, and then it will be actually mounted on the arbor, and it will be expanded by spring so that there could be a pressure, small pressure on the honing sticks, okay, or the lapping stick in this case, and it can be, the internal hole can be lapped, although the internal holes are rarely lapped, okay, because it is a very slow process. So, the objective of okay, now fine, here I hope it is understood that these are the processes which are actually the processes belonging to the abrasive processes, all right. And here we will stop for the discussing the abrasive machining processes, and next to that we will be discussing the economics of machining, because if you remember initially what we said is that the idea of producing a part is to make the part with the right accuracy, okay, right shape, size, finish, and of course, it has to be of the right kind of a cost, right cost. So, the objective of machining is to produce a component of required dimensions and surface finish at minimal possible cost, that I said. Okay. Now, the factors that can be varied during the machining operation to change the cost are speed, feed, depth of cut, tool and work materials, tool geometry, cutting fluid and so on. What is said here is that our idea will be to have a minimum cost of the product, okay, so that we can compete in the market. So, the components that we have said, we have found out that these are the cutting speed, this is the feed, is the depth of cut, or the cutting parameters overall, tool and the workpiece material, tool geometry, cutting fluid and so on. So, you understand that if we have the cutting speed more, for example, in that case the time taken is less, okay, and more products will be made within the given time, and the product cost will be decreased as a result finally. Similarly, the feed, okay, similarly the depth of cut, similarly the tool and the workpiece material, because if the tool material is very costly, in that case of course, the product will be costly, final product will be costly. Similarly, if the workpiece, if the blank will be costly, that material, basic material, then you cannot afford to produce a component at a lower cost and so on. So, overall what we are saying is that we can identify the parameters, okay, which can be actually regulated so that the cost could be minimum, okay, and cost minimum is that you can actually compete in the market with another manufacturers of the same kind of parts. Now, the technical data regarding speed, feed and the depth of cut are usually not available, okay, and their optimum selection cannot be made from the cost consideration alone. Okay. Now, an optimum cutting speed always exists, as I said that speed increases, okay. So, your time for the production is less, you are making that very fast, all right. So, that within stipulated time more products are made, okay. But what happens to the tool is that at a higher cutting speed the tool wear also will be fast, okay. But tool is expensive. So, that means for the same part, okay, you are incurring more cost in the tool as you are increasing the speed, okay. So, therefore, you cannot infinitely increase the speed, because in that case you have to pay more for the tool, okay. So, you have to have a compromise. So, that compromise we are saying as the optimum cutting speed. Always there would be an optimum cutting speed for the minimum cost, okay, where you will not have more tool wear, as much tool wear, so that the cost becomes very high, or it will not be as slow, so that the time taken is very high, okay. It will be an optimum value of the cutting speed, so that the cutting at that cutting speed the cost could be minimum, okay. For each application there is an optimum cutting speed, therefore, which would mean a compromise between the production rate and the tool cost, as I explained, okay. Now, the cost of machining is minimum at a particular set of cutting conditions. Now, this is about the speed we said. Same thing we can say about this, about the feed, about the depth of cut, because we have shown actually in the tool life through the Taylor's tool life equation, or rather through the modified version of the Taylor's tool life equation, that on the tool life you will have the effect of cutting speed, feed and the depth of cut. So, therefore, all these three parameters, cutting speed, feed and the depth of cut, they actually will regulate, and they can be regulated to obtain the minimum cost. Okay. Now, for simplicity we will only consider the case of single pass straight turning operation and obtain the value of optimum cutting speed. Although we said that of course, the on the cost there will be effect of cutting speed, feed and depth of cut, all three parameters, but it will be very difficult, or it will be very complicated to analyze all these three and take care of all these three parameters. But I will show you the analysis to get the minimum cost for only one parameter, that is a cutting speed, and I will tell you that how similarly you can get the optimum parameter for the feed and the optimum value for the depth of cut. Okay. Let us see. Now, let us assume the simple turning operation of a cylindrical bar. Okay. Let us say the cylindrical bar is of this type, where the diameter is capital D and the length is small l. Okay. So, we are turning that. Now, to do that, the important cutting parameters are the cutting speed, feed and the depth of cut. Okay. Now, the technological aspects, they include the what will be the surface finish, okay, what is the power requirement, what are the forces acting and so on. So, these are the technological aspects. Now, economical aspects on this, that so far we have not discussed, because we have discussed the important cutting parameters, cutting speed we have discussed, feed we have discussed, depth of cut we have discussed, okay, in the tool life and tool wear section. Surface finish we will be discussing, power requirement we have discussed, force we have discussed, these are the technological aspects. Now, in the economical aspects we have the minimum production cost criteria, maximum production rate criteria and the maximum profit rate criteria. What is said here is that we will have a particular optimum value of the cutting speed or feed or depth of cut, as we said. Now, with that optimum cutting speed we can have the minimum cost. Okay. Now, similarly, for if we want to have the maximum production rate, there also we can get an optimum value. All right. But as you understand that these two optimum values will be different. Okay. For one value of the optimum speed we can have the minimum cost, but we may not get the maximum production rate using the same optimum value of the cutting velocity. Same thing happens with the feed and the depth of cut, and also with the same values for which we are getting the minimum cost and the maximum production rate, we may not get the maximum profit rate. So, for maximum profit rate we may have a value which is different from the other two values. So, this is going ahead, I should tell you that we can have the optimum parameter for the cutting speed, feed and the depth of cut, for which the cost will be minimum or production rate will be minimum, production rate will be maximum or profit rate will be maximum. Let us see how we can get it. Let us have the designations that capital R is the cost per piece of the finally produced part. Okay. Here the R1 is the material cost per piece. Okay. R2 is the settling plus ideal time cost. Material cost per piece, you understand that this is the basic material, raw material which is required for making the final part, that is to add value to the raw material so that the final part can be obtained. R2 is the settling plus idle time cost. This is not ideal time, I am sorry, you can correct it that this is IDLE, idle time, when the machine does not work. okay, machine is not working. So, settling plus idle time cost is the one where the operator needs to clamp the part, okay. Operator needs to change the tool, to put that in at a certain angle, all right, make the adjustment in the tailstock if it is required, because the part can be also mounted on the centers and so on and so forth. All these adjustments, this is the settling, and that time the machine does not work, okay. But for that time which is spent on that activity, you are paying, okay, you are paying to the operator. So, therefore, that time has to be included. R3 is the machining cost per piece. So, machining cost per piece, you understand that for the entire machining process, the certain time elapses, and what is the cost of that time. By cost of that time, I mean that you are incurring some overall expenditure for the entire process, okay, entire production, all right. So, within that, let us say you can find out that how many parts are being made in a month or in a day or on an average, okay, and on one part how much, you know, but that particular part how much is being paid. This can be calculated easily. So, of course, there are economists, okay, engineers, economists, they actually calculate all those things. R4 is the cost of the tool changing per piece, okay. During the machining of one piece, how many times the tool is being changed, okay. Maybe one tool is worn out, this is to be changed, this is to be reground, or after the turning you need to do the chamfering, for chamfering you need another tool. So, you are changing the tool. So, this is the cost of tool changing, how much tool and how much it is cost for this thing, that tool changing per piece. And finally, the R5 is a tool cost per piece. Let us say one tool is full tool is required to make a piece, okay. After that, that tool cannot be used, all right, or one tool can be made, can be used for 5 tools, sorry, 5 work pieces. So, the tool cost will be in that case 1/5 for that particular part, okay, per piece. So, this is the tool cost, because each tool costs it has some value. Now, the small t5 we will say as settling plus again idle time per piece, okay. This is IDLE, idle time per piece. Capital T is the tool life, okay. TCT is the tool changing time. This we are designating that small ts is the settling and idle time per piece, okay, and cost is R2 for that time. Now, the T is the tool life, TCT is the tool changing time, and T small m is the machining time per piece. So, how much time it is required to machine that, and here if you see R3 is the machining cost per piece. For machining the entire part, how much cost you have incurred, because you know the machining time per piece, okay. Lambda 1 is the overhead plus labor cost per minute. Let me explain what is that overhead and the labor cost. Labor cost, you understand that the person who is working, operator who is working, he needs to be paid salary and the other expenses, okay. And the overhead is everything else that is required to be paid for the production of those parts. For example, it is the premise, it is the building, okay, the maintenance of the building, the capital cost of the building, all right. Then it is the electricity, then it is the hydraulics, then it is the water, then it is the pneumatic cost, and all the costs which are incurred for making that particular product, particular part, okay, for per piece, let us say, sorry, per minute, let us say. Now, the lambda 2 is the tool cost per grinding. Now, one tool may be ground 5 times, let us say, okay. So, tool cost per grinding will be the cost of the tool divided by 5 per grinding, okay, because after 5 grinding it has to be thrown out, it cannot be used. So, for each grinding the tool cost will be the cost of actual tool divided by the times that it can be ground. Okay. Now, the frequency of tool changing in production one piece, okay, we have the Tm, which is the machining time, that if we divide by the tool life, then you can find out that how many times we have to change the tool for making that part. Okay. Let us say, as I gave you an example, that one tool is required for making the entire, we are not changing any tool, okay, for the one part. It may so happen, or it may so happen that one tool is changed because it is worn out, all right, and that frequency can be found out from the machining time and the tool life, and the ratio of the machining time per piece and the tool life, this ratio is the frequency of the tool changing in producing one piece. Okay. Then in this cost per piece R, we have therefore all the 5 costs, that is material cost per piece plus the settling and the idle time cost per piece, idle time cost, sorry. Then we have the machining cost per piece, then we have the cost for tool changing per piece and the tool cost per piece. This is what has been shown, that the tool cost is actually tool cost consists of all these 5 costs. Okay. Now, let us see one by one. First one, the R1, you understand that this is the basic material, raw material I said. So, material cost is R1, that is not dependent on the cutting conditions or the cutting speed particularly, because we will always keep in mind that what we said here is that we are trying to get the optimum value of the cutting speed, one of the parameters, okay, for getting the minimum cost. So, to get the minimum cost, we are trying to find out what is the cost per piece, each piece how much it will cost. Okay. So, material cost does not depend on the cutting conditions, and it remains as a constant with respect to if you take that as a function of the cutting speed. Okay. Now, the setup and idle time cost, it is also independent of the cutting condition, particularly the cutting speed that we are considering, as well as the cutting feed and the depth of cut. Okay, because whatever is your cutting speed, this is idle time, or this is the tool changing settling time, you understand that. So, on that V or F or D have nothing to do, all right. So, therefore, it is also constant, but the setup and idle time cost will be equal to the overall which you are paying, that is the lambda 1 we said overhead plus labor cost per minute, and how much you are spending for the, how much time you are spending for setting up and the idle time. So, lambda 1 if we multiply by this time, it will give you the setup and idle time cost. Okay. Similarly, the machining cost, if you see, the machining cost is R3 here, and that R3 will be given as similar to this, what will be the machining time, okay. This is Tm machining time, and for that machining time how much you are paying, and this payment is the labor cost and the overhead cost, as I explained to you, both together. Okay. Now, the Tm is the machining time. Tm, as you know, we have already derived that earlier, that this is given by L, which is the length of this. Okay. Okay, here it is small l, let us say we are taking as the capital L as the length of the part, okay, divided by F and the N. So, let us say that this is the cylindrical part and this is the length which is L, okay. This is the diameter which is D, and this rotational frequency is N, okay. F is the feed. So, V c, that is the velocity, this is pi d n, okay. And here it is by 1000 because it is the minute to second. So, L by F n is given as the machining time. Okay. In here the n can be replaced by the cutting velocity with this formula, and then how to proceed further, that we will discuss in our next session of discussions. Thank you for your attention.